All right, in this lesson, we're going to explore what we call the end behavior of rationals. We've done at this point in the year end behavior of polynomials. So you may recall what we mean by end behavior is what happens when x gets really large as we move out towards the ends of the graph. This particular function models the number of turkeys in a forest, and often rational functions are used to model populations. Let's call this f of x in the text here since I left that out. F of x models the population of turkeys in the forest, and the question is, what seems to be the number of turkeys that can survive in the forest, right? So there's probably only so many turkeys that can survive in the forest before they eat all the turkey food. I don't actually know what turkeys eat, but one would expect that only a certain number of turkeys can survive in the forest. This, by the way, is what a turkey looks like. I know we're city people in here, so we probably don't see these very often. I did, however, just pull this up because in this other tab I have graphed our rational function f of x. And what we notice, right, is that f of x seems to approach a certain y value. So no matter how far I zoom out, no matter how big I make my x, f of x never gets bigger than, it looks like 5, right? My y values are getting closer and closer and closer to 5. So let's sketch that. So my function, it had a y-intercept, but it was down here somewhere. Doesn't really matter what it is, but it should never get bigger than 5. So I'm going to draw this dotted line, and it just kind of snuggles up to that line. So the answer to my question seems to be 5. It's 5,000 turkeys, right? Can survive in the... And notice that value shows up in the function, right? And we call that value 5 the leading coefficient. So that's the coefficient on the largest power of x in the numerator. This line y equals 5 is a horizontal asymptote of f. So what that asymptote is a line that represents that value that our function is approaching. So just like a vertical asymptote, our function kind of snuggles up to that line without actually touching it. And what we're interested in exploring here is, when do functions have these asymptotes? When do they not? And how do we figure out what the equations are? By the way, this word approach, that word is related to another concept we've been studying recently, so if that pricked your ears up, that's a good thing. Let's look at some other cases here. I've given you the graphs. Let's see if we can't figure out what the relationship is with the function and with the end behavior of the graph. Okay, so the first one we could say, as x approaches infinity, f of x approaches, it looks like it's going up forever, right? So I'd say also infinity. My second one, it's a little zoomed out so it's hard to see, but notice it kind of travels along the x-axis here. So I'd say as x approaches infinity, f of x approaches 0 in this case. And for horizontal asymptotes, remember our first function had a horizontal asymptote at y equals 5. My second function has no horizontal asymptotes. It just keeps growing forever. My third function has a horizontal asymptote at y equals 0. Right? So some of our polynomial vocabulary is going to help us describe these relationships, actually. So the degree of a polynomial is the highest exponent of x that shows up. Right? So for example, we'd say our numerator and denominator here are both degree 2. And our leading coefficient we already talked about, that's the 5 on the x squared in this case. So it's the coefficient. So notice our first function, our turkey function, the degree of the numerator and the degree of the denominator are the same. They both have x squared. And 5 shows up in the numerator. Case number 2, the degree of the numerator is bigger. Case number 3, the degree of the denominator is bigger. So we have a degree 3 versus a degree 1. Okay, that's the relationship we're exploring. Okay, It's sometimes called the principle of dominance. You don't need to know that it's called that, but I think it's helpful because the bigger power, whether it's on the top or the bottom, determines where the asymptote is or if it has an asymptote at all. So this is saying case 1, B bigger than A. That means the bottom is bigger. We call this bottom heavy. And the horizontal asymptote is 0. And the example of that we had was equation 3, function 3. Because we had x on top and then 2x to the third on the bottom. That one's bigger, right? A equal to B, that means it's the same power, right? So that was our turkey function, and that was 5x squared over x squared, and our asymptote was 5. We'll talk about how to fill this out here in a second. Number 3 is our top heavy fraction. A is bigger than B. That was equation 2. And we had x over x squared, I believe. Sorry, x squared over x, I should say. Top was bigger. Our horizontal asymptote did not exist. Okay, so the first 2 rules are pretty easy. If the fraction is bottom heavy, the horizontal asymptote is 0. The fraction is top heavy, the horizontal asymptote does not exist. And that makes a lot of sense, right? Because here the top is growing much faster than the bottom, so my function is increasing. Here the bottom is growing much faster than the top, so the function is not increasing, right? It's staying close to 0. But how do we figure out the horizontal asymptote for when they are equal to each other? Well, our turkey function kind of leveled out at y equals 5, right? And where that number comes from is the ratio of the coefficients, so 5 over 1. So in this case, C over D. And that's because the x's cancel out. So it would be cx to the a over dx to the b. If we know a and b are the same, those just cancel, just like my x is canceled over here. So that's how we find these horizontal asymptotes. It's 3 rules to remember, right? But I think they're pretty easy to remember if you remember the bigger power of x dominates the smaller powers. The last thing I want to add, and I hinted at this earlier, is that this limit notation means the same as horizontal asymptotes, right? So the limit as x approaches infinity is the same as what we just did, just written a different way. So what I like to do here is I like to circle my highest power of x on the top and bottom, and this limit is going to equal, I can make myself this note over here, 5x squared over x squared. In this case, these cancel out, and I can say the limit as x approaches infinity of f of x is equal to 5. Here, notice my highest power of x is bigger. I have a top heavy fraction. We can say this limit, remember this is my graph that grew forever, is equal to infinity. And then here, I have a bottom heavy fraction, right? My power of x on the bottom is bigger. This limit is equal to 0. Okay, so same rules, different notation. We're going to practice both.